Good afternoon, everyone. The topic of my paper is research on preparation and properties of CSHPG1000 phase change composites, including these four parts. Abstract. In this paper, composite material CSHPG1000 was prepared by multi-scope porous material CSH export and phase change material PEG1000 by melting blending, so that it can reduce hydration heat of cementitious system, utilizing the characteristic of releasing and storing energy of PCM. TEM, IR, DSCBD, and various other characterization methods were used to discuss the feasibility of CSH as support and investigate the morphology, pore structure, and stability of the CSH-PG1000 composite. The change of hydration heat and features of pore structure, as well as its effect on compressive strength, was also tested when the composite was added into the cementitious system. Introduction. PCM has been widely applied in various fields, owing to their high latent heat storage density, small volume changes, and fixed phase change temperature range. For constructions, suitable phase change material can also be used to solve the problem of thermal stress caused by the massive release of hydration heat in short term. The abacus simulations illustrated in the figure 1 demonstrates the concrete adiabatic temperature rise and thermal stress distribution, in which highest initial internal temperature is up to 70 degrees centigrade, and nearly 40 hours accosted to cool down completely. So, the proposed research of CSHPG1000 is of importance and necessity in building material field. Results and discussion. The calcium to silicon ratio was captured at 1.5. The multi-score pore structure of CSH was obtained by building a CSH model between particles and atoms at different scores, which provided theoretical basis for its rationality as a carrier. Prepared CSH is 21 micrometers, approximating to a normal distribution shown in figure 3. For composite, part of PG1000 entered and fills the internal pores of CSH, and part is wrapped on the surface of CSH. As a result, the particle size of the composite shows a bimodal distribution with average size of 45 micrometers. SEM and TEM exhibited in figure 4 shows the cluster of CSH composed of nanosheets and the pores between the randomly oriented clusters, forming a 3D network structure. Subsequently, it could be found in figure 4C and D that PG1000 changed the morphology of CSH when incorporated into it. The morphology presented in the yellow circle can be seen that PG1000 molecules embedded in the hollow space of CSH perfectly. Namely, PG1000 is loaded on the multi-score pore structure of CSH to form a compact and dense CSH PEG1000 block by blocking and filling the pores. Most importantly, no leakage is observed, confirming the stability of composites. Even after dozens of thermal cold circuit treatment, there was little leakage of PG1000 can be seen, suggesting that the PG1000 is well impregnated into CSH pores. The porous characteristic of the CSH and the CSH-PG1000 is examined. The results suggest abundant specific surface area and a wide range of pore size distribution. This multi-score pore structure enables CSH to carry amount of PCM of different particle size. When PEG is introduced into CSH, the pores of CSH larger than 4 nanometers are almost completely contained by PG1000 molecules. The steep decrease in specific surface area, pore volume, and pore size combined with the electron microscopy results proves that the PEG1000 could indeed fill the multi-score pores of CSH. Combination with the support can change the texture and morphology of the PCM, providing convenience for the incorporation of PCM, so that many problems of incorporation of single-pore PCM are avoided. Therefore, it's necessary to introduce PCM support into the cement-based composite material. As mentioned above, the structure feasibility of composite using CSH as a support is proved, which provides a premise for the perfect filling and stable composite. To achieve the aim of efficient energy storage. Compare with PG1000 and CSH. No obvious new peaks generating in the air spectrum of composites, conforming to the result of XRD. The physical bonding reaction between the CSH and PG1000 is controlled by the weak van der Waals interaction force. DSC and TG technology are conducted to investigate the thermal stability of CSH-PG1000 in variable temperature environments for long term, to ensure that the composite can service in the cement system effectively. Until temperature reached to 120 degrees, the mass loss rate of CSH-PG1000 composite is less than 5%. Shows that it has good thermal stability and environmental adaptability. The thermal stability properties was performed for 50 thermal code circles. It is remarkably noted that the form stable CSH-PEG1000 shows good thermal reliability and bonding stability regarding to its slight change in phase change temperature and latent heat. As a complement, there are no significant fluctuations in the zeta potential data under the conditions of different solution. Therefore, the combination stability and chemical stability of the support CSH and the new prepared composite are verified. This strong evidence suggests that CSH-PG1000 composite is chemically, thermally, and structurally stable during the storage and release of latent heat. CSH-PG1000 is placed in the cement system to test its hydration heat, compressive strength, morphology, and pore structure. With the content of CSH-PG1000 raised up to 20%, the existence of phase change material reduces the hydration heat of cement system and slows down the hydration process to some extent, indicating that CSH-PG1000 could play a good role in energy absorption and storage. Compare the compressive strength. There's an optimal dosage of 10%. For the later, strength after 14 days will not be affected. While for the samples with poor PEG1000 without support CSH, the compressive strength decreases significantly, about half of those with composite. The results indicate that the combination with CSH for peg1000 can satisfy the strength requirements when used in cement system, so taking advantage of CSH as support is necessary. For high dosage of CSH peg1000 replaced cement, the cementitious products in the pores and microcracks are reduced, and the texture is more loose. Therefore, skin more pore volume and area when the content of PCM gradually increases. Porosity, compactness, these microscopic experimental results are consistent with the macro experimental record mentioned above. Here comes the conclusion. For reasons of time constraints, I will not go into details. Thanks for listening.